This is the second 3.1 video, and it's primarily going to cover correlation. We'll talk about what it is, understand its properties, how it's affected by outliers, how to calculate it with a calculator, and how to explain why it's not causation. So correlation, what is it? It measures the direction and strength of the linear relationship between two quantitative variables. It is always a number between -1 and +1. If it's negative, then it indicates that the association is negative, and R is our symbol for correlation. So if R is greater than 0, it's positive, it has a positive association. The weakest a correlation can be is 0. The strongest a correlation can be is -1 or +1. If the correlation is 1 or -1, then these are going to be perfectly linear relationships. Let's take a look at 6 examples here. This first one is a graph of correlation of 0 because they are scattered out fairly well. But as they get more tightly scattered or clustered in a linear pattern, the correlation you can see here is now up to 0.3, and it's got this negative association. So here they get even tighter. This is a correlation of 0.5, and it's positive. Correlation of -0.7, correlation of +0.9, and -0.99. So you can see as they get tighter, tightly clustered in a linear pattern, the correlation is going to strengthen. So I want to look at a couple of specific examples to teach you a little bit more about correlation, and I'm going to do that with an applet. So with this applet, I'm going to put my points here in this area, and it's going to tell me the correlation up here. So if I put 2 points, then you can see the correlation is as strong as possible because any 2 points make a line. But if I keep adding in these points, you can see how the correlation changes over to the left. This is definitely a positive relationship, and it has a correlation of 0.68, so it's moderately strong. If I were to add a point way up here, this is going to weaken the relationship. It's going to weaken the correlation because now my data is more scattered and it's not as tightly clustered in this linear pattern. So you can see it dropped to 0.2. But if I drag this point down here, it reinforces that positive association. So points that spread the data out weaken the correlation, and points that reinforce the trend strengthen them. So you can see if I add a point here, this is going to reinforce that positive relationship and jumps up to 0.8 for the correlation. If I were to add a point down here, again, it's going to weaken it, cuts it nearly in half. Let's see what happens if I add a point right in the middle of it. So 0.72, basically, if I add a point right here, then these points here don't have too much of an effect. They don't weaken it, they don't strengthen it a whole lot. It doesn't change very much because they are right in the midst of it. But these points out further in terms of X have much stronger pull on the correlation. You can see it's going to jump much higher to 0.82. And if I do it down here, reinforcing this positive trend, it's also going to strengthen it. So these points that are outliers in terms of X have more influence on the correlation. Correlation doesn't tell us the whole story though. If I were to make a cluster like this that has a correlation of about 0, pretty close to 0, then if I add a point up here like I have been, it's going to drastically increase this correlation. And so now, if I didn't have this graph and I just saw that the correlation was 0.89, in my mind, I'd be thinking that this is a strong, positive, linear relationship. But this doesn't appear to be strong, positive, and linear. This seems to be very weak with one high outlier. But these outliers have a strong influence on the correlation because correlation is not resistant to outliers. So correlation doesn't tell us the whole story. We need to see a picture. Another example would be if I had a graph that looked like this. My correlation is extremely weak. negative 0.0. I can make it even weaker maybe. No, that strengthened it. There we go. So this is correlation of almost 0, but you can see that there is definitely some type of relationship going on between whatever these two variables would be. The issue is correlation measures linearity. So this is not a linear relationship, so correlation doesn't help us with this. So you might look here and say there's absolutely no relationship if you didn't have the graph. So it's important that you have a graph along with the correlation in order to get the full picture. So based off of the applet that we just did, I want to look at a data set from the SEC so that we have the team and the number of points on average they scored, and then we have the number of wins they had from the season. So you can see there is a positive, strong relationship in the graph. And I want to teach you first how to calculate what the correlation is. So we're gonna have to use our calculator and put our points in list 1 and put the wins in list 2. But it's really important that you note Alabama's points have to match up with their number of wins for your calculator to do this appropriately. Arkansas points have to match up with wins in the calculator. So in my calculator, I'm going to stat edit. I'm going to type in the average points in list 1 and their number of wins in list 2. So after I've typed them in list 1 and list 2, I just want to make sure that they're matched up as according to the table from the notes. So just pick a random one, 25.5, should be matched up with 7, looks to be right. So from here, before I show you how to find the correlation, I want to show you how to make a scatter plot. So we're going to go to our stat plot, second y equals, go into our first stat plot, make sure it is turned on. And you can see the very first one is a scatter plot. So my X was in list 1, my Y values were in list 2. So if I hit zoom 9, it's going to give me that scatter plot that you saw on the notes. So now to calculate the correlation, I'm going to go to stat, calculate, and then linear regression line reg AX plus B. When I hit enter, explanatory variables in list 1, responses in list 2. Hit calculate, and your calculator right here may give you R, or correlation, but if it does not, like mine, then here's what you need to do. You need to turn on your diagnostic on, and there's 2 ways to do it. First way, you can just hit mode, scroll down to find diagnostic on. So there is stats diagnostic, turn it on, and then second mode, you should be good. You can do it there. The second way, if your calculator for some reason can't do it that way, just go to your catalog. So hit second 0 to go to your catalog, and then scroll down to find the letter D. So I have my alpha on, so I'll hit X to negative first, take me to the D, and diagnostic on. Hit enter, and then it'll just say done, and you're good to go from there. So now, if I do stat calculate linear regression using those 2 variables, it should give me R and R squared. So R, remember, is correlation of 0.936. So I'll copy this down from what we just did on the calculator. So this correlation is strong. It reinforces the positive linear relationship between points per game and wins. We could also say that as the points per game increases, the number of wins increase as well. So now I want to talk about this specific point, question B. It's Mississippi. What effect does it have on the correlation? Justify your answer. So based on the applet activity that we did, does this point reinforce the overall trend of the graph, or does it weaken it? Does it make it more scattered? So when I look at this, this point is low in terms of X, so it's going to have more of an influence because it's a bit of an outlier-ish. And so this is really reinforcing this overall trend. from the bottom left to the top right, this positive trend. So this is going to strengthen the correlation. Another way you could justify it is if we remove this point, then the overall pattern would be more scattered and not as clustered in this linear pattern. So again, Mississippi strengthens it. If it were removed, the remaining points would not be as tightly clustered in the linear pattern. Go ahead, pause the video if you want, and see if you can estimate what you think the correlation is for these graphs here at the bottom. So you can see these graphs are getting weaker and weaker as we move from left to right. So here's the formula to calculate the correlation. And you'll never have to do this because you can do it on your calculator. But I do want you to see that this formula here looks familiar, doesn't it? Observation minus the mean divided by the standard deviation. This is simply just the z-score of the x value times the z-score of the y value, and then we're going to add it to all of the other points. So each point you calculate the z-score of the x and the z-score of the y, multiply them together, and add them all up, and then divide by n minus 1. That's how you calculate the correlation. So what I want you to know is correlation is not going to have any units because they're just standardized scores that are being used. So finally, I want to talk about a couple of facts and highlights that I've shown through this video regarding correlation. And one thing that I haven't actually said yet. Correlation makes no distinction between explanatory and response variables. So that means if you switched x and y, the correlation would be the same because they're still related in the same manner. Because R uses standardized scores, R does not change when we change the measures of units. So if we converted one of our variables from feet to inches, then the correlation is still going to stay the same. Just because we've changed the units doesn't mean the correlation is going to change. Correlation itself has no unit of measurement. Correlation does not imply causation. The reason for this is there are other variables that could be at work. For example, it is known that there is a strong and positive relationship between the number of casualties at a fire and the number of firefighters present at the fire. So does that mean that more firefighters going to the fire are causing more casualties? No, there's something else at work. The fire is bigger. The larger the fire, the more firefighters have to be there. And the larger the fire, the more casualties there are. So the fire is what's causing it. It's not the number of firefighters. Just because they're correlated does not mean they're causing the other one to happen. Correlation has to be between only quantitative variables. Correlation does not describe curved relationships between variables, no matter how strong the relationship is. We looked at a good example in the applet from that one. Just because the correlation is close to -1 or +1, it doesn't guarantee it's linear. You need a graph to be able to get the full picture. Correlation is like the mean and standard deviation. It is not resistant to outliers, strongly affected by them. And then finally, correlation is not a complete summary of two variable data. Like I've said many times, you need to have a graph, a scatter plot as well.